Let's look at applying what we know about integration to a few different types of problems. So with some of these ones, we're going to be looking at integration problems involving motion. Okay, so if we remember that the rate of change of position with respect to time is the velocity. The rate of change of velocity with respect to time is acceleration. And so what we can do is we can work in the opposite direction by integrating. So here we have a particle starting from rest, and it is 3 meters from a fixed point. Okay, so if we think about this might be the fixed point. Now 3 meters from that fixed point might be, say, here. And so that would be 3 meters at that point. And it's moving in a straight line with an acceleration of a equals 6t plus 8. So it's just moving in this straight line. Okay, we want to find its position and its velocity at time t seconds. So this is our acceleration. We first will find our velocity by integrating our acceleration. So velocity would equal the integral of acceleration with respect to time. So we can find the integral of 6t plus 8 dt. And so then it's 6t squared over 2, which becomes 3t squared plus 8t plus a constant of integration of c. So our velocity is given by this rule. Now, we know that at time t equals 0, our velocity is equal to 0. We know that because it says it starts from rest. So, in other words, 0 equals 3 times 0 squared plus 8 times 0 plus c. Obviously, from that we can see that c, our constant, is equal to 0. And so that means our velocity is equal to 3t squared plus 8t. Okay, over on this side here we'll work through to find our position. So position is the integral of velocity. So if we just think of position as, say, x, because we're just travelling in this straight line, so x will be equal to the integral of velocity with respect to time, which is going to be the integral of 3t squared plus 8t dt. So 3t cubed over 3 gives us t cubed plus 8t squared over 2, which is 4t squared, plus, we'll call this constant d, seeing how we used c over here. Now we know it starts from rest at 3 meters, so if we say this 3 meters over here, because it's a positive value of 3, let's just make an assumption here that say that's the positive direction, whereas that would be the negative direction to the left. So we can say that if t equals, or at t equals 0, x equals positive 3. And so that means that we can see that if t equals 0, these two terms become 0, x equals 3, that means d must equal 3. So we can safely say that our position is x equals t cubed plus 4t squared plus 3. So we have our velocity and our position equations at time t. So that's the principle what we're working with here. All right, let's apply what we know then to the next question. So here we've got the rate of change of position, which is velocity. Okay, velocity is the rate of change of position of a particle travelling in a straight line given by this rule here. So dx dt, or we could say v equals dx dt equals 40 minus 10e to the negative 0.4t meters per second. Clearly, time t must be greater than or equal to 0. So we've got our position in meters and our time t in seconds. So A, initial velocity when t equals 0. V must be equal to 40 minus 10e to the 0, because negative 0.4 times 0 will be 0. Probably get rid of that there. Okay, so with that in mind, that means our velocity is going to be 40. That should be actually, sorry, and e to the power of 0. Okay, so that becomes 10 times 1, which is 10, so that gives us 30 metres per second. Okay, B, find the velocity after 10 seconds. So when t equals 10, our velocity, or our rate of change of position with respect to time, is going to be 40 minus 10e to the negative 0.4 times 10, which we can see is going to be 40 minus 10e to the negative 4 as an exact value, and that corresponds to an approximate value to 2 decimal places of 39.82 metres per second. Okay, part C simply says to find the total distance travelled by the particle in the first 10 seconds. It's worthwhile thinking about the shape of this curve. Okay, so for the derivative, it is, okay, so it's a reflected in the y direction, so in the y-axis, reflected in the x-axis as well, having both negatives here. So normally our exponential curve goes like that, but because it's reflected in so a reflection in the y would mean that it looks like that, and reflected in the x as well as the y means that it's going to be like this, and because it's translated up 40 units, it's going to be up here. So between 0 and 10 seconds, okay, so it's going to kind of look like this. That's our velocity, that's our time, and between 0 and 10 seconds, we're actually looking at, remember, so our distance or our displacement really is the area under the curve. So the total distance travelled will safely be our definite integral from 0 to 10 of 40 minus 10e to the negative 0.4 t. Okay, so then that's going to be 40 t plus 10 divided by 0.4, which is going to give us 25 e to the negative 0.4 t. And we'll need to substitute 10 and 0. That gives us, when we substitute the 10 first, that's 400 plus 25 e to the negative 4, and then minus, substituting our 0, that becomes 0, and that then leaves us with minus 25 e to the 0, which is 1, so just minus 25. So then we have 375 plus 25 e to the negative 4 as an exact value that approximates to 375.46 metres. That is the total distance travelled in the first 10 seconds, corresponding to the area under that curve. Okay, let's look at this last example. So here we have a stone projected vertically upwards from the top of a building 20 metres high. So here, let's just imagine we've got this building. Okay, it's 20 metres from the ground to the top of the building, and then a stone is projected straight up. Eventually it's going to reach a maximum and then come back all the way down to the ground. We know that because here it says find the time taken for the stone to reach the ground. So it's going up and then coming back down to hit the ground. So it's got an initial velocity of 15 metres per second. Okay, so we're going to use calculus to do this. We're not going to use the equations of motion. Okay, so the time taken for the stone to reach its maximum height. Let us begin by noting that the acceleration due to gravity, this is assumed to be negative 10 metres per second squared. In other words, it's 10 metres per second squared, but in the downward direction. Okay, so our A is negative 10. So then our velocity is going to be the integral of negative 10 dt. Okay, so velocity then will be negative 10 t plus c. Now we know that it has an initial velocity of 15 metres per second. So if t equals 0, velocity equals 15, going up, so it's the opposite direction of the acceleration. So that means our c, constant here, must be equal to 15. Okay, so we can say then our velocity is equal to negative 10 t plus 15. Okay, we want to know how much time is taken for the stone to reach its maximum height. Now we know that when it's going to reach its maximum height at this point here, okay, at that point the velocity is 0 because it's not going up, it's not coming down. So if v equals 0, then 0 equals negative 10t plus 15. 10t must equal 15. T must equal 1.5 seconds. Okay, so that's how long it takes to reach its maximum height. B, find the maximum height. So we need an equation, we need a rule that calculates the height, okay, or the position, if you like. So the height, we'll just use h, is going to be given as the rate, or rather we know that velocity is the rate of change of that height, so our height will be the integral of our negative 10t plus 15 with respect to time. So h equals negative 10t squared over 2, so negative 5t squared plus 15t plus d. Now we know that the height starts, if we can assume that, say, ground 0, at the ground level, that's a height of 0, so it starts at a height of 20. So if t equals 0, then our height is equal to 20. Then that means these two terms become 0. That means d must be equal to 20. So our height is negative 5t squared plus 15t plus 20. Okay, so then what are we wanting to find? The maximum height reached by the stone. So if we know the maximum height occurs when t equals 1.5 seconds, so if t equals 1.5, then h, our height, is going to be negative 5 times 1.5 squared plus 15 times 1.5 plus 20, which if we calculate that, negative 5 times 1.5 squared plus 15 times 1.5 plus 20 is 31.25 metres. So that is the maximum height. Maximum height is 31.25 metres. Okay, the time taken for the stone to reach the ground. Okay, so here we have a height equation. So now the ground level has a height of 0. So let's let h equal 0. So then 0 equals negative 5t squared plus 15t plus 20. Okay, we want to solve this quadratic. Let's make it simpler by dividing throughout by negative 5. So then t squared minus 3t minus 4 equals 0. If we factorise that, we'll have t minus 4t plus 1, which means that t must be equal to 4 or negative 1. Clearly, we're not going to have a time of negative 1, so this is our time for it to reach the ground. Okay, so the question says time taken for the stone to reach the ground. It's going to be 4 seconds. All right, last question here. Velocity of the stone as it hits the ground. Well, we know the time, so then we can use our v equals negative 10t plus 15. And if t equals 4, then v equals negative 10 times 4 plus 15, which is negative 40 plus 15, it's negative 25 metres per second. And obviously, so the relevance of the negative means that the velocity is heading in the downward direction. Velocity of the stone as it hits the ground is 25 metres per second. If you want to specify the direction, which we should, for being a velocity, is down. And that's it. Okay, so there are some problems to work on. MathsQuest text 9J or the yellow text 9J, questions 7 to 18. Okay, they are all